How is everyone? Chatty today. Yeah, that's good. So nobody's falling asleep today, right? All right, after lunch, cool the room off a little bit so it'll be a little, we want to put folks to sleep in here with a hot room. All right, so welcome back to Dr. Julius Siegler and to our series, Stepping Stones in the Development of Modern Physical Thought. And today you see James Clerk Maxwell, or we have decided that it kind of looks like Ken West. But we're going to talk about, or Julius is going to talk about electromagnetism today. Right. Before he does, a couple of quick announcements. One, if you have not already heard, I did announce it in Confab, Dr. Neil Summerlin has postponed his spring program, hopefully to the fall. So we're hoping that'll still take place. He's having some health issues, so just keep him in your thoughts. Also, Amy Merrill Willis from the University of Lynchburg has agreed to do a 3-lecture series on green spirituality. And I've got a room full of scientist people. I don't know if that interests you, but green spirituality is sort of an earth-based religious, earth-based religion for humans is how she describes it. So if you're interested in that, just keep a look at your weekly and your March monthly. So Julius, I'm going to turn it over to you.
Okay. Thank you, Susan. Thank you all for coming. Before I start, last time we were talking about magnets, and Polly Garby was kind enough to bring some moderately strong refrigerator magnets. Now, I do this in my classes all the time, pass them around, let people actually experience magnetic forces. So I'm going to pass these around and play with them while I'm talking, and I'll collect them at the end. These are moderately strong refrigerator magnets. The ones that I use are strong enough to where little kids can't pull them apart, or they get their fingers pinched when they do try to pull them apart. So I wouldn't do that to you. Okay, we've been talking about scientists, obviously, over the course of the last few months. And as I think about the history of particularly physical science, but the history of science in general, I think about the scientists whose work has actually changed the way we look at the world. And most of the people I'm going to talk about are in that category. You could begin perhaps with Aristotle, even though his science was weak. His thought impacted human thought for 15 centuries or more. Galileo certainly got things started and could be included in this group. You could certainly include Charles Darwin in the biological sciences, and perhaps even Karl Marx in the social sciences as people whose views have had profound impact. But in the physical sciences, there's Isaac Newton and Albert Einstein, who I'll talk about in a couple of weeks. And the third one, in my estimation, is James Clerk Maxwell. And he is the one, I think, that is least recognized, least known to the general public. And yet, he is the person whose portrait, along with that of Isaac Newton, sat on Einstein's mantle throughout his adult life. Einstein said, "I stand not on the shoulders of Newton, but on the shoulders of James Clerk Maxwell." Another colleague wrote, up until the time of Maxwell, science was dealing with a mechanical world. And after that, we'll see. The sort of question type thing here implies that Maxwell provided a bridge between the mechanical world of levers and pulleys and springs and things that were part of the clockwork universe and the modern way we think about physics and the world in the 21st century. Every mobile phone, every television screen, every electronic device you use uses the same principles that Maxwell enunciated in his significant papers in the 1860s. So I'm going to spend some time talking about Maxwell as a person briefly, and then I'll come back and say a little bit more about his science. And I will state at the beginning, I'm heavily indebted to the biography written by his lifelong friends Lewis Campbell and William Garnett in 1882 for much of the information that I'm going to share with you. It's curious, there are dozens of biographies of Einstein, at least 10 good biographies of Faraday, lots of biographies of Newton's, and the most recent biography I could find of Maxwell is 25 years old now, and there's none that is regarded as definitive. Maxwell was born in Edinburgh, Scotland, in this house on India Street, which is now owned by the Maxwell Foundation, in 1831. And shortly after his birth, his family inherited the country estate of Glenlair, which is in south west Scotland near Dumfries. And if you look carefully, you can see that the part that's on your left was burned out in the 1920s and has not been repaired to this day. As the Maxwell Foundation recently was able to purchase the property and is in the process of restoring it. His father, a man named John Clark, adopted the surname Maxwell when he inherited the estate. And although he was landed gentry, John Clark Maxwell was a practical man, one who designed his son's own square-toed shoes for comfort, who cut and sewed his son's clothes, who designed the extensions on the original house that go off to the right and built them largely with his own hand. And in his diary, John, his father's diary, we find him talking about cutting out his shirts and his son's shirts while planning those outbuildings. He not only planned them, but he made he built them with his own hand, as I said. As a young person, James Maxwell, the son, was, quote, very happy. This is from an uncle, and has much improved since the weather got moderate. He has great work with doors, locks, keys, etc., and his show me how it do's is never out of his mouth. He also investigates the hidden course of streams and bell wires, the way the water gets from the pond through the wall and a pond or a small bridge and down a drain. Lewis Campbell, one of his biographers, wrote, and this is a quote, "Before seeing this letter, I had been told by his cousin, Mrs. Blackburn, that throughout his childhood his constant question was, what's the go of that? What does it do? Nor was he content with a vague answer, but would reiterate, but what's the particular go of it?" He entered the Edinburgh Academy in November of 1841 at the age of 10. And prior to that, he'd been homeschooled. And you can guess that a young man with homemade country clothes and square-toed shoes was going to be out of place in a prep school. Because of his appearance, his quiet demeanor, and the fact that he was not as well prepared as his classmates immediately tagged him with the nickname Dafty, which he never seemed to resent. Again, according to Lewis Campbell, who became his closest friend during the time at the Edinburgh Academy, at school he gradually made his way. He soon discovered that Latin was worth learning and the Greek dialectus interested him when we got so far. And there were two subjects in which he at once took the foremost place when he had a fair chance of doing so. These were scripture, biography, and English. In arithmetic, as well as in Latin, his comparative want of readiness kept him down. On the whole, he attained a measure of success which helped to secure for him a certain respect. And however strange he seemed to be to his companions, he had three qualities which they could not fail to understand: agile strength of limb, imperturbable courage, and a profound good nature, end quote. P.G. Tate, who's an eminent scientist of the same period and a lifelong friend and colleague and a classmate behind Maxwell at this Edinburgh Academy, recalled that, quote, "At school he was at first regarded as shy and rather dull. He made no friendships and spent his occasional holidays in reading old ballads, drawing curious diagrams, and making crude mechanical models. This absorption in such pursuits, totally unintelligible to his schoolfellows who were then totally ignorant of mathematics, procured him a not very complimentary nickname, which I've already said. About the middle of his school career, however, he surprised his companions by suddenly becoming one of the most brilliant among them, gaining prizes and sometimes the highest prizes for scholarships in mathematics and English verse. At the age of 14, Maxwell wrote a mathematical paper in which he generalized the concept of an ellipse. And we talked a little bit about ellipses when we talked about Kepler many months ago as a particular mathematical form. Maxwell's father, who regularly attended meetings of the Royal Society of Edinburgh, sent the paper to a member of the society who read it and forwarded it to others. They agreed that the paper had merit and, quote, on the description of oval curves and those having a plurality of foci, end quote, was read to the Royal Society of Edinburgh by a member of the society in April of 1846. They thought it inappropriate for a 14-year-old to appear before the society. Maxwell entered Peterhouse College at Cambridge in October of 1850, but soon moved to Trinity College, where he believed it was easier to obtain a fellowship. Again, I'm going to quote from P.G. Tate's article recalling Maxwell. He brought to Cambridge a mass of knowledge which was really immense for so young a man, but in a state of disorder appalling to his methodical private tutor. The student, to a great extent, took his own way, and it may safely be said that no high wrangler of recent years ever entered the Senate House more imperfectly trained to produce paying work than did Clerk Maxwell. But by sheer strength of intellect, though at the very minimum of knowledge of how to use it to advantage under the pressures of the examinations, he obtained the position of second wrangler and was bracketed equal with the senior wrangler in the highest ordeal of the Smith's prizes. Wrangler is a term, I guess, that was applied to mathematical students who were in these competitions, and the Smith Prize was the highest prize in mathematics at Cambridge. Another friend and colleague, an eminent physicist, describes Maxwell's undergraduate days. Scholars dined together at one table. This brought Maxwell into daily contact with the most intellectual set at the college, among whom were many who attained distinction in later life. These, in spite of his shyness and some eccentricities, recognized his exceptional powers. The impression of power which Maxwell produced on all he met was remarkable. It was often much more due to his personality than to what he said, for many found it difficult to follow him in his quick changes from one subject to another. His lively imagination started in so many hairs that before he had run one down, he went off on another. Many of his colleagues commented on his sense of humor. I think I've mentioned this at a previous one in response to Dr. Potter, or maybe Dr. Potter mentioned it. At one point during his youth, he was living in a boarding house, and his landlady was a gardening enthusiast, and she brought home a new plant, which she showed to everyone who would look at it. That evening, Maxwell purchased a larger version of the plant and switched it with the original. The next morning, his landlady was excited to see how much the plant had grown overnight and called everyone to see. He repeated that exercise nightly for the next several days, and every morning the ever more excited landlady called everyone to this the remarkable growth, and then he reversed the process. And he wrote verse. Some of his colleagues claimed that had he chosen the literary path, he would have been a poet equal to Burns in stature. But most of and you can find his poetry and published in a volume, and it's very interesting to read. Some of it's very funny. Another type of practical joke, he did a series of studies on the rotational motion of tops. Now, you don't play with tops, so at least most of you were of a generation that didn't play with real tops, where you took a string and spun them down on the floor. But Maxwell was studying how that thing would move, and he had a top that would spin for almost 45 minutes. And one day he had visitors. He set it spinning, and the visitors were overnight visitors. They went to bed, and the top was spinning. The next morning, he got up early and set it spinning again, so that when they came down for breakfast, they thought it had been spinning all night. And when he was a professor at the University of Aberdeen, he wrote to a friend, "No jokes of any time are understood here. I've not made one for 2 months." Anyway, Maxwell obtained his fellowship and graduated with a degree in mathematics from Trinity College in 1854. And he remained at Cambridge for graduate study, tutoring until he was awarded a fellowship by Trinity College to continue his work. In early 1856, his father became ill, and wanting to spend more time with him, he applied for the post of professor of natural philosophy at Marischal College in Aberdeen. Maxwell traveled to Edinburgh for the Easter vacation of 1856 to be with his father, and the two went together to Glenlair. But on the 3rd of April, his father died. And shortly after, Maxwell returned to Cambridge as he had planned, and before the end of April, he learned that he had been appointed to the chair at Marischal College. So that November, Maxwell took up the appointment in Aberdeen. And when the subject announced by St. John's College of Cambridge for the Adams Prize of 1857 was the motion of Saturn's rings, Maxwell was immediately interested. He and his friend P.G. Tate had thought about the problem of Saturn's rings while still pupils at Edinburgh Academy. Now, the problem with Saturn's rings is that nobody knew what they were. Galileo had observed that Saturn appeared to have lumps on both sides. As the telescope was improved, a better picture showed that there were rings around that planet. And even in the early 1830s, photographs showed that there was a division in the rings. And photographs also showed that the rings were no more than about 40 miles thick. So you've got these rings, and the conjecture was, what are they? Are they solid? Are they made up of particles? Nobody knew. So Maxwell spent some time thinking about that, and his research during the first 2 years at Aberdeen resulted in the idea that the stability of the rings could only be achieved if the rings consisted of numerous small solid particles. That's an explanation that was eventually confirmed by the Voyager spacecraft more than 100 years later. In a letter to Lewis Campbell, written in 1857, Maxwell wrote, quote, "I have effected several breaches in the solid ring, and now I'm splashed into the fluid one amid a class of symbols, SYM, symbols truly astounding. When I reappear, it will be in the dusky ring, which is something like the siege of Sebastopol conducted from a forest of guns 100 miles away and 30,000 miles the other, and the shot never to stop, but to go spinning around a circle of radius 170,000 miles. The paper won the Adams Prize, and another brilliant physicist, Airy, who was a colleague, wrote, it was one of the most remarkable applications of mathematics to physics that I have ever seen. So, this is what the young James Clerk Maxwell looked like. And then he became engaged to marry Catherine Mary Dewar in February of 1858, and they were married in June of 1859. Despite the fact that he was now married to the daughter of the principal of Marischal College, in 1860, when Marischal College and King's College combined, Maxwell, as the junior person of that department, had to seek another post. His scientific work, however, had been proceeding with great success. Professor Stokes had written to him in November saying, "I have just received your papers on the dynamical top, etc., and the account of experiments on the perception of color. The latter, which I missed seeing at the time when it was published, I have just read with great interest. The results offer most remarkable and important evidence in favor of the theory of three primary color perceptions. a theory which you and you alone, so far as I know, have established on an exact numerical basis. So he's on his way to a very successful professional career at this point. And I should tell you that, like Michael Faraday, James Clerk Maxwell was a seriously religious person. He was a member of the Church of Scotland. He grew up in that church, and he maintained an affinity and a relationship with the church throughout his life. And I mentioned scripture biography. I'm not sure exactly what that is. Perhaps somebody can tell us afterwards. But he has many, many letters on interpretations of scripture and on his philosophical / religious beliefs, something that isn't necessarily obvious when you just pick up a biography of him and that was sketches out his life as I'm doing now. So in 1860, concurrent with the beginning of the American Civil War, Maxwell was appointed to the chair of natural philosophy at King's College in London. He was 29 years old. The 6 years that Maxwell spent in this post were the years when he did his most important experimental work, although the duties of the post were more demanding than those at Aberdeen. Campbell, his biography, writes, "There were 9 months of lecturing in the year, and evening lectures to artisans, etc., were part of the professor's duties." In terms that you might understand, he lectured for 15 hours a week, which is consistent with a modern 5-course teaching load. You won't find many serious scientists at major universities teaching 5 courses a semester. And he lectured 3 nights a week to artisans, local members of the community, on various topics of interest to them. And he did his research. Maxwell left King's College in the spring of 1865 and returned to his Scottish estate, where he continued to refine his thoughts on electricity and magnetism. He made periodic trips to Cambridge and rather reluctantly accepted an offer from Cambridge to be the first Cavendish Professor of Physics in 1871. He designed the Cavendish Laboratory as well as most of its instruments and helped to set it up. Again, for those of you who don't know, the Cavendish Laboratory, which is the Department of Physics at Cambridge University, is one of the foremost laboratories in the world. 30 Nobel Prizes have been won by members working in that laboratory. The part of the electron was discovered in the Cavendish labs, the neutron. The structure of DNA was worked out in the Cavendish laboratories, just to name a few things. It got its start with the instruments and designs set up by Clerk Maxwell. Late in 1878, he had become terminally ill with stomach cancer, which is the same thing his father died of. A colleague who attended Maxwell's last lecture course at Cambridge wrote, "During the time in May 1879, Maxwell's health evidently began to fail, but he continued to give his lectures up to the end of the term. To have enjoyed even a brief personal acquaintance with Professor Maxwell and the privilege of his oral instruction was in itself a liberal education. Nay, more, it was an inspiration, because everything he said or did carried the unmistakable mark of a genius which compelled not only the highest admiration, but the greatest reverence as well." He returned with his wife, who was also ill, to Glenlair for the summer. His health continued to deteriorate, and he suffered much pain, although he remained remarkably cheerful. On the 8th of October in 1879, he returned with his wife to Cambridge, but by this time he could scarcely walk. One of the greatest scientists the world has ever known passed away on the 5th of November, 1879. He was 48 years old and at the height of his intellectual powers. Curiously, this was the year of Einstein's birth. His doctor said, quote, "No man ever met death more consciously or more calmly." So that's a picture of the man, and it doesn't really do him justice. I mentioned that one of the things that his classmates admired at him at the Edinburgh Academy was strength and agility of limb. Maxwell was a natural runner, and he would run through the streets of Cambridge or Aberdeen or wherever he was on a fitness regimen daily, which is almost unheard of in the middle of the 19th century. Many, many aspects of the man that are worth noting. He is buried in a churchyard not far from Glenlair, his house in southeastern Scotland. And that's a simple marker that marks his tomb. Now, Maxwell had always been interested in color and light and began to study it seriously while at Trinity College. Chiefly, he wanted to know why mixing different colors of light produced different results to mixing different colors of paint. Now, again, most of you are aware that there are two different sets of primary colors, one that are called additive, those are the ones that light technicians use in the theater, and one that is called subtractive, which are the ones you learn in elementary school, red, blue, and green, where you mix paint and you mix it all together and you get black. You mix all the light primaries together, you get white light. That had been thought about and experimented on by Thomas Young and Heinrich Helmholtz, both of whom had theorized that the human eye contained 3 color receptors, although the precise mixture of colors they responded to had not yet been demonstrated. Maxwell's experiments projected an image through 3 filters, red, green, and blue, and these projectors were then aligned by Maxwell to display a color image. This is the 3 images that he used, and you can't really tell what they are because it's not very clear. But he used this color wheel to photograph through as the 3 filters. You see the red, blue, and green. The drawing on the right is difficult to interpret, and I won't say anything about that. And the result was the first color photograph of a tartan ribbon. Again, the colors are not vibrant, but they are there. I have in my memory, and I could not find it, a photograph that I saw of one of the early Voyager spacecraft, one of the first spacecraft to land on the moon and send back images. And you may recall that those images were black and white because the color TV cameras could not travel that distance. They're too bulky. But on one of the legs of the Voyager spacecraft, there was a color wheel. And they photographed the lunar surface through red, green, and blue filters, sent back 3 different images through red, green, and filters, then recombined the light to get the first color images of the moon's surface. So the same technology, basically, that Maxwell had done. The Maxwell color triangle, as it became known, formed the basis for the chromaticity chart released in 1931 by the International Governing Body on Color. Another quick aside, he also did significant work in the field of statistical physics. If you think about the molecules of gas in this room, which you probably don't very often, there are a lot of them. Remember that there are, you learned in high school chemistry something called Avogadro's number, which is a very large number, almost unintelligible to our minds, except in some kind of mathematical notation. And those molecules are constantly banging into each other. And Maxwell decided that the only way you could really talk about heat and thermal motion is to use statistical averaging. And one of the things, one of the probably 50 items in physics that carry Maxwell's name is something called the Maxwell-Boltzmann distribution, which is the natural distribution of molecular speeds in this room. If you know the temperature of the room, you can actually draw a distribution which is kin to the normal distribution that most of you study when you take statistics, the bell-shaped curve, except this one's not bell-shaped because the most probable distribution is not the median distribution. The most probable velocity, is not the median distribution. So he worked out that and many implications of that, and would be highly regarded if that had been all that he did. Okay, that's a major piece of work that I'm not going to spend any time talking about. It's the fields of electromagnetism that he really changed. We talked the last lecture about Michael Faraday, perhaps the greatest experimental physicist in history. And Faraday, working at the Royal Institution of London, did significant research in electromagnetism as well as in chemistry. And based on his observations of the forces between magnets and electric currents, he invented the first electric motor. And then he asked a research question, which is in many ways the characteristic of the way physics progresses. And the question was something like this: if electricity in the form of electric current can cause magnetism, can magnetism cause electricity? And answering that question required a significant portion of Faraday's adult life. But he did find that by experiment that magnetism can generate electricity, and in the process he invented the electric generator. I should also point out that the American scientist Joseph Henry was doing significant experiments along the same lines at the same time, but with a very different point of view, and overlapped in some ways the work that Faraday did. Now, here's where things begin to change in the way physicists think in the history point. Newton had ducked the question of gravitational attraction by simply saying that somehow a mass like the Earth reaches through empty space and exerts the pull on the moon to cause the moon to orbit the Earth. He called that action at a distance. He didn't like it, but he didn't have any better explanation. And he was able to describe the force quantitatively and calculate the orbit and do all kinds of wonderful things. But the problem is still there. How does the moon know that the Earth is here and vice versa, 250,000 miles away and pulling as if connected by some kind of giant cable? Faraday envisioned the interaction between magnets and between electric charges as being transmitted through what he called lines or tubes of force, crudely analogous to invisible rubber bands stretching through otherwise empty space and pulling and pushing on the charges or magnetic poles. He further introduced the idea of a field. The idea is that a charge or a magnet somehow alters the space around it, and if you bring another charge into the area, it interacts with that altered space and not directly with the thing that's creating that altered space. So you can make the same argument in a gravitational sense. The Earth somehow alters the space around it, and the moon interacts over here with that altered space, and that interaction is in the same of a force. Well, at a very young age, Maxwell became aware of Faraday's work, and there's a significant amount of correspondence, extant correspondence between Maxwell and Faraday that is preserved in the collection of the Cavendish Laboratory. And one of his most important achievements was his mathematical analysis and extension of Faraday's concepts in magnetic lines of force. His paper called On Faraday's Lines of Force was read to the Cambridge Philosophical Society in two parts in 1855 and 1856. And he was able to show that a relatively few simple mathematical equations could express the behavior of electric and magnetic fields and their interrelation. At that point, he was 23 years old. a year out of Trinity College. Although he had derived these mathematical relationships through use of an elaborate mental mechanical model, again, he's envisioning something mechanical through space doing this, he eventually realized that the model wasn't really necessary, that the only thing that was necessary was the fields themselves, and to regard those fields as real physical entities. He essentially reduced everything that was known about electricity and magnetism to this series of equations that related the sources of these phenomena, electric charge and current, to the fields and the fields to each other. Now, this is a fairly common physics t-shirt, and I'm getting a little bit ahead of myself, but those are the equations, and I'm going to come back to them in a minute. And you want to see this later and understand why the last sentence is there. Here are the equations, and don't panic about this. I couldn't explain them to you in a week, probably. Actually, I could. But look at them as you would something in a museum, just for curiosity. And I'm going to tell you what they are and what they say. The top one is, I have to look at this to see what is on the top. Because I can't see the screen from here. The top one has an electric, the word E, symbol E for electric field, and on the right-hand side it has a Greek letter rho, which is a form of electric charge. And basically it says that the only source of a stationary electric field is an electric charge. So if I've got an electric field out here that is not changing, the only source of that is some kind of array of electric charges that are not changing. That's all it says. Now, one of the reasons that Maxwell, and by the way, Maxwell never wrote these equations, not in this form. The mathematics that you see here, the symbols were developed by an American scientist named Josiah Willard Gibbs late in the 19th century. This is the form that they're in. Each of those equations represents three equations, one for each of the three coordinates in space, left, right, up, down, front, back, or X, Y, and Z in mathematical language. So each of these equations is really three equations. Furthermore, from a calculus standpoint, each of these equations is called a partial differential equation, which means that it's one step above differential equations, which are one step above calculus that you normally learn in a one-year calculus course. Again, it's standard math, but it's something that is hard to explain without going to a blackboard and really working through it. So the first one is pretty simple in terms of what it says. The second one says that there is no analog to an electric charge for magnetism. In other words, there is no magnetic pole. Magnets always come in dipoles, north and south, linked together. There is no wandering around North Pole. There are wandering around positive charges, and there are wandering around negative charges, but there is no analog for that for magnetism. Then you have Faraday's law, which says that the source of a time-varying electric field is in fact a time-varying magnetic field. In other words, magnetism can cause electricity. Simple enough. And again, the implications of that equation are pretty broad. And then the last one is called the source of a time-changing magnetic field is twofold. One of which is electric current. That's the thing that says J on it. The other one is a time-changing electric field. That's something Faraday never thought about. The fact that you can create magnetism by having a rapidly varying electric field was an addition that Maxwell made to these equations, experimentally determined. So everything we know about electromagnetism is embodied in these equations. All of the experimental work that's done, everything that you use that uses electricity is governed by these equations. That's pretty powerful. Now, if you notice that there are these equations some have a B, which is a symbol for magnetic field, some have an E, which is a symbol for electric field, and some have both in the same equation, meaning that the electric field depends on the magnetic field and vice versa. They're called coupled differential equations. Now that generally causes some consternation to solve. However, it's pretty easy to combine those equations and eliminate either the B or the E from them by substitutions. And I'm not going to go through that. But it's a fairly straightforward thing. When you do, you get the same equation for the electric field that you get for the magnetic field. They're the same form. The only difference is whether you have those little mu's or these little epsilons and those little symbols, squiggly symbols that are down in the bottom equation that I haven't said anything about yet. And it's the same equation, but it describes the electric field and the magnetic field. Now, Maxwell was a pretty good mathematician, and he recognized that equation as something he had seen before. He recognized it as a form of what we call the classical wave equation. It's the equation that describes the motion of sound waves, the equation that describes the motion of water waves, the equation that describes the motion of vibrations through any medium. And the classical wave equation had a velocity term in it that tells you where the velocity of that wave is. The velocity term appeared as a combination of that little epsilon and that little mu with a subscript 0. Those are constants that are fundamental electromagnetic constants. The constant little epsilon, the thing that looks like a little e with a 0, is called the permittivity of free space. And it's a constant that appears when you calculate the force between electric charges. It was measured and known at the time. Not as accurately as it's known now, but it was measured. The quantity mu0 is called the permeability of free space. And it's a constant that appears when you measure the magnetic force between two magnets, repulsive or attractive. Those two constants were well known, not as accurately as they are now, but when Maxwell put the numbers in for those two constants, the velocity of that wave, that electric wave or magnetic wave, was essentially the same as the velocity of light. So Maxwell had discovered on his own, quite unexpectedly, that light, which was not well understood at all, was a form of electromagnetic disturbance, electromagnetic waves. Now this is all done theoretically. He never generated electromagnetic waves. But it's a remarkable result, a mathematical result, a theoretical result. But there's a problem that it solves. Experiment had demonstrated conclusively that light is a wave, and what we call a transverse wave, a wave in which the actual motion of the wave is perpendicular to the direction that it's moving, like a water wave. The water goes up and down, the wave goes sideways. And there's incontrovertible experimental evidence that that's the case, but nobody knew how to solve the problem of what medium it was moving through when it moved through empty space. people, and in fact Newton had posited that the existence of something called the ether, this fluid that filled empty space and provided a medium. But the problem is that physically the speed of a wave is determined by, let's say, the rigidity of the medium. The softer the medium, the slower the wave moves through it. The example I used to like to do, and when I could get it, was to get a tray of dining hall Jell-O, the green kind, about a foot long. They slice it and start this end moving, and watch the wave propagate down, which took some time. That's a slow propagating wave. Sound moves much more rapidly through steel than it does through air. So the speed of light is pretty fast. That means the medium out there had to be, if you thought about it as a fluid, had to be almost infinitely rigid. And yet stuff moves through it easily without any friction. The moon keeps going, planets keep going. So now we have a medium. This electromagnetic field is the medium. This disturbance that is caused by the appearance of the charges is the medium that propagates these waves. And only in the last few years have we demonstrated the existence of gravity waves. Same kind of argument, different phenomenon, but same kind of argument. So this is a really incredible discovery. I'll say a little bit more about it in a minute. This is just a recapitulation of that. One other thing that did come out of it was the notion that accelerating charges radiate electromagnetic waves. So if you've got a charge that is going around in a circle, it's accelerating just like the moon is accelerating, falling towards the earth all the time. It's constantly radiating energy. We get bursts of energy from interstellar charges that are being accelerated as they get closer and closer to a black hole. We see these X-rays. We get bursts of energy. We get periodic energy from a rotating neutron star, which is doing the same kind of thing. So this is the basis for antennas. Electric charges move up and down in the antenna. They're constantly accelerated. They generate electromagnetic waves. Those waves hit another antenna. They cause the electric charges to accelerate up and down and create electric currents, which can be turned into sound or light and other things. So not for Maxwell, but as part of Maxwell's heritage, is this entire electromagnetic spectrum. We are sensitive to a very small part. You see the color bands in there, but that's misleading. The actual part of the spectrum that we're sensitive to lies between those two arrows, between infrared and ultraviolet. It's a very small band. Everything else that's on here is an electromagnetic radiation that had never even been suspected prior to Maxwell. About 20 years after Maxwell first published this, Heinrich Hertz, a German scientist, demonstrated the existence of radio waves for the first time. 10 years later, Marconi invented the first wireless transmitter, the first radio. Prior to Maxwell, invention was usually something that led the science. James Watt invented a steam engine. He had no idea of what thermodynamics was because it hadn't been invented yet. In fact, the whole science was developed as an attempt to make steam engines more efficient because they realized that the energy present in the coal and stuff that they were burning was mostly going up the stack. And after Maxwell, people began to look at the science and then see what can we invent based on the science. The other thing that's changed radically is the time between a scientific discovery and its appearance as a marketable product has been compressed dramatically over the last century. Well, let's see where else we got here. This is Maxwell shortly before he died, sitting in his laboratory. Again, photography had been invented about the time of Faraday's work as the director of the Royal Institute, and it had become much more common by the middle of the 19th century. This is a plaque that appears on the Faraday house in Edinburgh. This is again a photograph. This engraving was done from a photograph taken again later in his life. This is the only statue that I can find a record of Faraday in Scotland. I mean, of Maxwell in Scotland. It was erected in Edinburgh in 1931 or so by the Maxwell Society. It's curious because in Glasgow and in other places there are lots of statues for people who are Scottish heroes, John Knox, David Livingstone, Lord Kelvin, who was a colleague of Maxwell's at Cambridge, James Watt, Robert Burns, William Wallace, Robert the Bruce, but one statue of perhaps certainly one of the greatest scientists who ever lived, and certainly the greatest Scottish scientist who ever lived. Maxwell was what I would characterize as a true Renaissance person. The biography that I alluded to earlier quotes extensively from his personal correspondence, and you wonder where he found time to write the lengthy letters. And the correspondence shows a man absolutely committed to his friends and family, a man who regularly returned to the liberal arts side of his academic training. He continued to read Latin and Greek. He talked about philosophy. He read Spinoza, Descartes, and even Kant's Critique of Pure Reason. His letters often contain verse that he had written, and they consistently reveal his deep commitment to Christianity. In 1882, his biography wrote that marvelous interpenetration of scientific industry, philosophic insight, poetic feeling, and imagination, and overflowing honor was closely related to the profound sincerity which, after all is said, is the truest sign alike of his genius and of his utmost nature, and is most apt to make his life instructive beyond the limits of the scientific world. And in his life, regarded as a whole, there is a depth of goodness which can be faintly indicated in his biography. Einstein said that the special theory of relativity owes its origins to Maxwell's equations of the electromagnetic field, and that Maxwell's work changed the world forever. Richard Feynman said that from a long view of history of mankind, seen from, say, 10,000 years from now, there can be little doubt that the most significant event of the 19th century will be judged as Maxwell's discovery of the laws of electrodynamics. The American Civil War will pale into provincial insignificance in comparison with this important scientific event. And finally, Carl Sagan, Maxwell's equations have had a greater impact on human history than any 10 presidents. And I'll stop with that. Thank you. So, any questions? I don't think that. Oh, this is the plaque. This is the plaque that appears in the Poets' Corner. I guess it's called the Poets' Corner of Westminster Abbey.
Is there a chicken and an egg answer to electricity and magnetism?
Yes. You have to bear with me, though, because that's, again, it's something I can't show you easily. But it turns out that once you have the tools of relativity, you can derive all of Maxwell's equations from the electrostatic equation that's called Ohm's law. So the electrical phenomenon is fundamental. The magnetism is a relativistic effect of moving electric charges. And that's, that blew me away when I first saw it. Yeah, but I have worked through it a couple of times with students, and it's actually not that tedious, but you do have to use the tools of relativity to get to that point. But it's for all practical purposes, they're on an equal basis. But only theoretically can you go from electricity to magnetism. You can't start with magnetism and go back to electricity from a theoretical standpoint.
Out of curiosity, what are the upside down deltas?
It means it's a symbol. It's called a vector operator, Greg, and it means a series of second partial derivatives
I understand.
with respect to x, y, and z. Some of them. That's where the partial differential equation comes in.
Yeah.
It's a vector operator, and that's another whole story. But one of the really forgotten people of science is Josiah Willard Gibbs, who was a late 19th century, early 20th century American physicist. And Gibbs worked in the area of thermodynamics. In fact, one of the things that's on display at the Cavendish lab is a model that Maxwell made of what's called a Gibbs surface in water. It's sort of like a phase diagram for water, a three-dimensional model. But Gibbs also invented vector calculus as we know it. Maxwell knew vector calculus without knowing all the symbolism that we use today. So if you read his book on electromagnetism, his treatise on electromagnetism, which I actually used not as a textbook, but as a supplement to my course textbooks in graduate school, because it's that clearly written, you would see 3 partial differential equations for each one of these, one for each set of coordinates. So vector calculus, vector analysis like this is extremely powerful in the sense that it gives you a very compact form, but it's also misleading in terms of how you unravel that to actually do stuff. And one of the reasons that it took probably 20 years before the scientific community really understood what Maxwell had done in 1855 and 1856 with these papers, because of the difficulty of unwrapping this math into forms that everybody could understand. He was a mathematical genius, no question about it. And in one of the letters I read, and I thought about bringing this in, but I didn't want to take too much of your time. But he was writing to somebody, and he said, in many ways, I think I would have been better off had I been more like Faraday and less mathematical, because it's too easy to go off on little tangents and so forth when I'm doing math. Oh, this would be fun to do. Let's go see what this does. And I mean, that's the way his mind worked. And everybody who ever talked to him talked about the fact that he would be talking along in a sentence, and all of a sudden it goes this way, and you got to try to figure out now what is he talking about, because the way his mind worked. Yes.
Was Maxwell, was he aware of the electromagnetic spectrum of the different areas that we now?
No.
No, not at all.
He just opened the door for that, because once you could show, once Hertz found electromagnetic radiation that was not visible light, radio waves, then others began to look at other frequencies, figure out ways to create frequencies and so forth, and it opened up. But it's like, would anybody have ever thought to invent a radio if they hadn't known about the possibility of electromagnetic radiation? You had to know that was possible before you could open it up. No, he didn't. There was no hint. X-rays had not been discovered. He was aware that that people's vision was the ends of your vision spectrum extend a little bit differently for every person. In other words, you may be able to see something at the red end of the spectrum that I can't see, just as you do in music. You probably can hear sounds that I can't hear at the top end of the spectrum and so forth. So he knew that, but he didn't know what lay beyond that. I mean, he was obviously aware that sunlight carried energy. I mean, they knew there was some kind of radiation there, but when it began to be called infrared or recognized as the same thing as light, I don't know. Yes.
Hold on, Ann.
You mentioned the connection between light and electromagnetic force, and I'm thinking about the eruptions that occur on the sun's surface and the aurora borealis that results from that. You want to comment something about that?
What is happening on the sun's surface are these huge magnetic storms that nobody exactly knows. There are models that may or may not be accurate in a long time. And those magnetic bursts put out intense magnetic fields. And the magnetic fields interact with the charged particle rings that are orbiting the Earth. And that does create radiation, which shows up as the aurora. The radiation that's circling the Earth is doing that because of the Earth's magnetic field. These particles are emitted by the sun as part of the nuclear fusion process that fuels the sun. And fortunately for us, because they could be damaging to us, the nature of the magnetic force forces them into an orbit rather than letting them come through to Earth. So yeah, there's a very definite relationship. There are also relationships which are less well understood between the magnetic activity or lack of magnetic activity associated with sunspots. Those are cool areas moving across the Earth's the sun's surface, but they also have a magnetic impact. And there's a correlation between sunspot activity and weather on Earth, but no cause and effect model that I'm aware of that is adequate. But yeah, absolutely. If you ever, the size of some of what appear to be flames shooting out of the sun is really staggering when you think about how large the sun is and how large that thing has to be visible as a separate entity on the sun. And it's not just aurora. I mean, it interferes with your cable signals and all kinds of things in addition.
Herschel had found infrared earlier with his work with prisms. Am I correct? But that hadn't been integrated into any systematic theory?
No. It was not known that it was the same as light or not. Yeah. And the terms infrared and ultraviolet were both there because, again, originally because of the variance in human eye sensitivity from person to person. One of the things I used to do with school kids is have them look at a spectrum of mercury. And there's a line in the mercury spectrum that is at the edge of the ultraviolet. And if you take a photograph of it, it shows up as a blue line. It's very bright. Most people can't see it. But I would have students look at the spectrum of mercury through a dispersive medium and use crayons to draw the lines that they saw. And many of the students would draw that blue line, but most would not. So yeah, there was an understanding that there was not a sharp cutoff as this optical part of things went. But again, in terms of electromagnetic field, Faraday had spoken about a field but had no theory of a field. And this is the first field theory that was put out. And the interesting thing to me is I read about it, and I've read some of the papers, not all of the papers that Maxwell wrote, is that he had this model, and I'd love to see what sketches he made as he was trying to work out this mechanical contraption to explain these charges attracting each other and so forth, and how he did the physics of it once he had the contraption in place. And then he says, well, I don't need all this stuff, and threw it away. And so let's just talk about the fields. It's remarkable to encounter to read about people who have this kind of mental acuity and breadth and curiosity that was constant throughout his life, and yet realize that he was not like some people who are at the top of their profession or close to the top of their profession. He'd take the time to talk to young students about things, very approachable during his time at all of these schools. And quite possibly would have discovered much more had he lived a normal lifespan. David?
Only child?
I think so, yeah. There may have been a child who died in childbirth, but yeah, he was the only child.
As was Newton?
Hmm?
As was Newton?
Yeah. And again, I didn't point this out, but Newton was born in the year that Galileo died. And so Einstein was born in the year that Maxwell died. And we'll talk about Einstein, I think, 2 weeks from today. Well, thank you again. I appreciate it. This is fun.